Hi, John here. Today we're going to do a slightly more advanced video about a wind turbine. I'm going to talk you through each of the main components and also a little bit more about the concept of how it works. So let's just play the animation now. And we can see the wind turbine is starting to turn. Now, when it starts to turn, it has to overcome an initial state of inertia. In other words, it needs a kick to get it started. This is what we refer to as starting torque. It requires quite a lot of energy to actually put a body into motion, such as to start a wind turbine turning. But once it's in motion, it requires far less energy. So now it's in motion, it's starting to turn, which means there's a slight breeze. Now notice that the turbine is sitting on top of a large modular tower. The reason that the turbine is sitting so high up in the air is because, due to the wind power density, we're going to extract approximately double the amount of energy at a 50-meter elevation than if we're at a ground elevation. So it really does make sense to build these towers relatively high in order that we can extract more energy from the wind. Now, the wind power density itself, which is what you would use to decide how much energy you can get out of the wind power density is heavily reliant upon wind speed. If you double the wind speed, you're actually going to increase the amount of power you can extract 8-fold. The reason is, if you look at the wind power equation here, if you increase the velocity slightly, you need to cube it. That means you're going to times it by itself 3 times. And that's going to give you a much larger number than if you didn't cube it. So the wind velocity is incredibly important. And by putting the turbine at a higher elevation, we'll get a higher wind speed, and thus we get a higher wind power density, and we can pull more energy out of the wind. Another thing to notice here is that the turbine has 3 blades. The reason it has 3 blades is because it's the optimal number of blades you can have for this type of turbine. You could install 4 blades, but this would add additional weight to the top of the tower, and the amount of energy you can extract from 4 blades instead of 3 is relatively little, so you're not really getting much increase in efficiency. In fact, you're getting hardly any. On the other hand, you could install just 2 blades instead of 3, but the downside with this is, in order to extract the same amount of energy as when you have 3 blades, the 2-blade rotor is going to need to spin a lot faster, and this adds quite a lot of stress to the blades themselves and also the tower. So the optimal number that engineers decided on is a 3-blade turbine. This specific type of turbine is called a horizontal axis wind turbine. And we can see that the axis of the turbine, it will run on a line through the turbine here, and that is called a horizontal axis wind turbine. The alternative type of wind turbine that you could see would be a vertical axis wind turbine. However, vertical axis wind turbines are simply not as efficient as horizontal axis wind turbines. Horizontal axis wind turbines rely upon lift. That means they're installed perpendicular or at a right angle to the direction of the wind. So as the wind flows across the blades, it imparts lift, or it causes lift upon the blades, and this pushes the blades in a certain direction. Now, just for clarity here, when we're talking about a force, we're talking about something that is pushing an object in a linear motion. That means straight ahead. When you start talking in terms of wind turbines, we're talking about torque, and that is a force applied in a rotary motion. So as the air is passing over these blades, which are actually called airfoils, it's going to impart lift, and this lift is going to cause a torque on the rotor. With a vertical axis wind turbine, we don't have lift, we have something called drag. Essentially what will happen is the wind will blow into a large cup-shaped area, and this will cause the turbine to rotate. However, it only rotates for about half of its cycle. For the other half of the cycle, it has to come back upwind, and this is where we lose the energy. So the wind is blowing into the cup, and we're harnessing that energy, and it's spinning, as you can see on the picture here, the turbine around. However, once it gets past a certain point, it has to go back upwind before it can start to harness the energy from the wind again. And this is why the efficiency is so low for a vertical axis wind turbine. And that's why you'll see horizontal axis wind turbines installed all over the world for large applications and not vertical axis wind turbines. We can see earlier I was talking about blades and that we've got 3 of them. These blades are often referred to as airfoils. Now these airfoils have the same shape as an aeroplane's wings. An airfoil, although it has a fancy name, essentially means that it has a shape that has maximum lift and minimum drag. So when you hear someone talking about an airfoil, that's all you need to say to yourself. Oh, he's talking about those things that have maximum lift, or they've been maximized for lift and minimized for drag. That's what an airfoil shape does. With an airplane, this is pretty handy because it enables you to get off the ground and go into the air. And with a wind turbine, it's also pretty handy because by maximizing the lift, you're maximizing the amount of energy you can extract from the wind. And obviously, the drag itself represents a loss. So if you can reduce the drag as much as possible, you can increase the amount of energy you're pulling out of the wind. The blades themselves are split into certain areas or certain terminology. You can see here we've got the blade root, that's this area on the right hand side. We've got the blade tip, which is this area on the left hand side. The leading edge of the blade is the bit that cuts first into the wind. We actually call this the angle of attack. That's the angle at which the blade encounters the wind first, and the leading edge will be quite round. So it helps to get the wind over the blade in a smooth manner. The trailing edge, which is around the other side here, is actually quite sharp. We can see it here pointing downwards. And that is so that the wind can flow past the blade and leave the blade as quickly as possible and minimize the drag, which represents a power loss. The blades themselves are actually twisted. And the reason we'll twist the blades is so that we can maintain the same angle of attack even though the blades themselves are actually rotating at different speeds. In fact, I should actually explain that a little bit better. The blades themselves aren't rotating at different speeds, but the blade root and the blade tip are actually coming into contact with the wind at different relative speeds. So we'll twist the blades slightly in order that the angle of attack can be maintained and we can pull out as much energy from the wind as possible throughout the blade's entire length. Now another thing I should mention here while we're up here is that the turbines, or a lot of the turbines that you will see, are white. Now there's a reason for this. One of the reasons is it's just not a very obstructive colour. If we look at the wind turbine from this angle, it actually blends almost into the background. Now if you live in the UK, where I grew up, it's pretty much always cloudy. So these wind turbines blend quite nicely into the background, especially if you're at ground level. We'll just zoom out and have a look from here. The other reason is it makes them a lot easier to spot if you're flying an aircraft. Although I should mention that these wind turbines are beginning to get so large that a lot of them will have to have lights on the top anyway in order that any aviation traffic can actually avoid them. Since we're back at ground level, let's have a quick look at the tower shape itself. Now this is a modular tube tower or circular tower. The other types of tower that you're likely to see on land would be lattice or a tripod type structure. Generally, this modular tubular shape here is becoming predominant. The reason is it allows you to assemble the wind turbine quickly when you're in the field, and it's also a relatively stable structure. The foundation itself will be reinforced concrete, and you're going to need a very strong foundation to deal with the vibrations and the actual weight of the tower itself and give it a firm and stable grounding. In fact, arguably the foundation itself is one of the most important aspects of the turbine installation. So once we've assembled the tower, we get up to the top and we're again looking at our horizontal axis wind turbine. The wind comes from this direction, passes over a rotor, passes over the blades or the airfoils, imparts lift, and then continues moving on towards the right side of the screen over the nacelle housing, which is this piece here. Now from this angle, you should be able to realize that if the wind is passing over the blades and some of that energy is being extracted from the wind and imparted onto the blades, the wind itself is actually going to slow down. Now there's a few other factors that are going to happen here. The wind itself is going to diverge from the blades, and as some of the energy has been extracted, it will slow down. But all of this means that the amount of energy we can extract from the wind In fact, it's limited to just below 60%, about 59.3%. The wind has to continue flowing past the blades in order that you can extract the energy out of the wind. However, as it goes past the blades, the wind is slowed down because some of its energy is imparted onto the blades. And this causes almost like a traffic jam type of problem. The wind to the left side of the screen can no longer pass across the blades as quickly as the predecessor did towards the right side of the screen. So we don't want this. Obviously, we still want the wind to keep flowing. We don't want to impair it or slow it down significantly that we can no longer extract any more wind. Okay, that's slightly over exaggerated there. You're always going to be able to extract some wind. You're not going to stop it completely. But my point is, you can only ever get to a rating of 59.3% efficiency because of this problem. Now, this efficiency rating of 59.3% is well documented and it's referred to as Betz's Law. Now, before we have a look at the internals of the turbine itself, let's talk about a few of the other things that we can see from the outside. Now, if I push the play button again, I'll just back it up slightly, we can see that the turbine is rotating in a clockwise direction. Now, this degree of freedom, or this movement, is actually on the azimuth plane. Now, this motion, as it changes so that the rotor continues pointing into the wind, this is known as yawing, and this represents another degree of freedom. So we've got the azimuth, which is the rotation of the blades itself, and then we've got yawing, which is the rotation of the entire head. That includes the nacelle body. Now, there's one other degree of freedom or degree of rotation here that is not so obvious, and that is the blades. The blades themselves are what we call control pitch, and it means you can adjust these three blades in order to change the angle of attack. And because you're changing the angle of attack, you can also regulate how much energy or how much torque is applied to the rotor itself. Now, this is pretty useful because if it's very, very windy and you don't want the wind turbine to turn, you want to put it into a safe position, what you can actually do is turn the blades to zero pitch so that they're extracting as little energy from the wind as possible. In other words, they're generating very, very little lift. And once you get to that stage, you can apply a brake to ensure that the blades don't rotate. So that's the 3 degrees of movement. We've got the clockwise rotation of the blades. We've got the yawing motion, which is rotation of the head. And we've got the rotation of the blades in their mountings, which adjusts the pitch. Let's turn this around now. We'll have a quick look at the internals of the turbine. Take a cross section. Might need to adjust this slightly. Okay, so we can see now the internals of the horizontal axis wind turbine.